We're going to go through each of the questions from the part 1 of the semester 1 final exam review. And this is mostly about limits and continuity. So we have a limit here, and we have to remember that the first thing we always do with a limit problem is just take whatever value this is for x and plug it in here. And in this case, it's meant to be a little bit tricky because you're going to look at that and you're going to say, oh, root x, root 4 here is going to be 2, and then I have a 2, that's going to give me 0. But it's actually a plus. You know, most of the time that's a 0, or that's a minus, so then you get a 0 in the denominator. You have to do something interesting. Here it's actually a plus, so we just plug that in. There's no problem at all. We get 4 in the denominator, and then we have 5/4 for our answer. Okay, moving on. That's a nice one to start with, as long as you remember to try direct substitution first, that is. Looking similar, however, this time, if we plug in the 4, we do in fact get 0 in the denominator, so that's no good. Often when I see a square root like this, especially where I have 2 terms in either the numerator or the denominator separated by plus or minus, and only one of them is a radical, the first thing I'm going to try to do is multiply by the conjugate. Now again, when we talked about this back in chapter 2, we said, you know, we're mostly familiar with multiplying by the conjugate to get a square root out of the denominator, so we sometimes don't think about it when the square root's in the numerator, but it's a helpful limit tool as well, so we just kind of have to remember that. So I multiply by the conjugate, leaving everything the same except for changing it a plus in the middle, and it's got to be the same thing in the numerator and denominator that I multiply by, so that I'm multiplying by 1. Now I multiply this out. I'm going to scooch it over here a little bit so I have some more room. So I have the limit as x approaches 4. The numerator, the reason that I do the conjugate is because essentially what I've created for myself here is a difference of squares. When you FOIL this out, when you distribute both terms, you're going to get the first term squared, the last term squared, and then those inner and outers are going to cancel out because of the plus and the minus. So I end up just with x squared minus the quantity 3x plus 4, because when I square that, all it does is cancel out the square root. The denominator, I'm not going to distribute this, because I'm hoping that when I simplify the numerator, I'm hoping that something is going to cancel out. And so that's kind of just the hope I'm hanging on to here, and I'm saying, well, it's going to cancel out if I leave it sort of factored like this, undistributed. And when I look at the numerator, I have to be careful of my negative sign, but because I want things to cancel, I need to then factor this. This is not factored. There's a minus here. Factored means everything is just multiplied, like in the denominator. So this numerator can factor limit as x approaches 4 of x minus 4x plus 1. Now I'm looking at this in the denominator, I'm thinking, brutal. I have x minus 4, they have 4 minus x, and that's not going to cancel. Well, I can just factor a negative out of this little guy, and that would change the sign on both of those. So I do that. Negative x minus 4. And then again, just leave this, don't multiply this out, hoping it will cancel. So now the x minus 4's do cancel. And so now I have, now after I've canceled that, I want to go ahead and double check, can my direct substitution work now? Originally I couldn't plug in the 4 because the denominator had this 4 minus x, and then that would be 0 in the denominator. Now though, I've canceled that part out. So if I plug in 4 here and 4 here, it's not going to give me 0, so I'm good to go. So I'm ready to do my substitution now. So this is going to give me 5 in the numerator, and then the denominator, this is going to be a 4, that's 12, plus 4 is 16, square root of 16 is 4, 4 plus 4 is 8. And, almost forgot my negative. Negative 8 So that's the answer there. Okay, cruising right along. Another one, plug in the 2 initially, and again you'll get a 0 in the denominator, so that's not what we want. So I need to try to factor and cancel. This time, not nearly as ugly as that last one. I can just factor this numerator and denominator. The numerator is x plus 3 times x minus 2. The denominator is x plus 2 times x minus 2. How nice, the x minus 2's cancel out. I can now plug in. I've eliminated the problem that gave me the 0 in the denominator, and I'm going to get 5 over 4. A lot of numerators of 5 here. Not a trend that we can expect on the actual exam. Alright, this one's a little different. The previous ones were simply evaluating a limit. Now they're asking us to actually think about something here. So the line y equals 5 is a horizontal asymptote for which of the following functions? Select all that apply. So what we have to remember here, this is in the limits section, so we think, oh, okay, limits. Remember that the definition of a horizontal asymptote, you have a horizontal asymptote at y equals, say, 5, if the limit as x approaches either plus or minus infinity, could be one, could be the other, could be both, of your function equals 5. As you go way out to the left or to the right, you look at the end behavior of that function. Your inputs approaching infinity are your outputs approaching one number. So I just need to consider each of these one at a time. As I think about plugging in bigger and bigger and bigger numbers to the numerator, I know that this sine wave is just going to bounce back and forth between positive and negative 1. This 5 in here is going to provide a horizontal compression, but that's not going to change the range. You know, if there was something multiplied out here, it would stretch my wave, but that's not happening. My y values are still between negative 1 and 1. My denominator, though, well, as I plug in really big numbers, it's just going to get really big. So I'm going to have a relatively small number, something between negative 1 and 1, divided by a huge number. Well, that's just going to get smaller and smaller. So this does have a horizontal asymptote, but at 0, not at 5. So, no. This next one, a little tricky to see. Sorry about that. Hopefully it's clear on your screen. But the denominator is an x cubed. The numerator is an x squared. So when we plug in our huge numbers, x approaching either positive or negative infinity, the denominator is literally going to be x times larger than the numerator. So you plug in 100,000, the denominator will be 100,000 times bigger than the numerator. So you have a relatively small number divided by a relatively huge number. Well, again, that's 0, not 5. Think about it again, plugging in huge numbers. We get 5 times a huge number divided by 1 plus a huge number. Well, when we're talking about huge numbers, this plus 1 doesn't really matter. So I can see that, yes, the numerator will be approximately 5 times bigger than the denominator. So my output will just continue to get closer and closer and closer to 5, the larger the x is that I plug in. So yes, that one works. Same thing will happen in the next one. This time both the x's are squared, but since they're both squared, we just look at that ratio because these things don't matter. When the x is big enough, x squared is just so much bigger than x that this doesn't matter. Even so much bigger than 7x, it just doesn't matter. So yes, this next one works as well. And then certainly not for this last one. That's just going to get bigger and bigger and bigger and bigger and bigger. So no. All right, moving on. So we've got a piecewise linear function such that the limit as x approaches 3 does not exist. Which of the following could represent that function? So it's basically saying, for which of these 3 does the limit as x approaches 3 not exist? And so we just consider each one at a time. Here, you just, again, I mean, they told us it's linear, but you just have a nice straight line and another nice straight line, and they switch at x equals 3. So the question really is, do we have a picture like the next one, where you have this jump when you switch from one piece to the next? Or do the two pieces actually meet? And the easiest way to figure that out is just to plug in 3 to each of these. Well, 12 minus 3 is 9. 4 times 3 is 12, minus 3 is 9. Hey, that works. We're all good. Oh no, but wait. Neither of these have the or equal to. So when I graph it, I'm actually going to get a hole there. But that doesn't matter, because the limit, by definition, only cares what happens when we get really, 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 really close to 3, but not equal to 3. And that hole is only at x equals 3. Everywhere else, we're good. So we are, in fact, the limit does, in fact, exist here. The function is not defined at x equals 3, but the limit as x equals, or the limit as x approaches 3 does exist. I'm looking for where it does not exist, so this one's not for me. Here, the limit does not exist. The limit as x approaches 3 from the left is 2. The limit as x approaches 3 from the right is 0. Those are not the same. So this one does not exist, and that's what I want. I want limits to not exist at x equals 3. Here, when we look at the table, my first reaction is to say, well, I don't know. It's just a table of values. These are just some crazy table. I don't know what happens in between. You know, maybe I've got something where you've got, you know, a whole here and then some other craziness here, and who knows what's happening. But if I look at these values, you know, because I just don't know what happens in each of these in between is the point we're making here. And this is often an important consideration. I don't know what happens in between these things. I don't know. But that's not true in this case. I also always have to come back. I said, my first reaction when I see a table, I don't know what happens in between each of these values. Could be anything. But let me go back and read and see if it told me anything about what happens in between. I've got a piecewise linear function. So as I look at this and say, okay, this is a piecewise linear function, well, then there really is only one thing that can happen. I have to go from 7/3 to 0, and then from 1 to 0, and I can see the pattern that's happening in my linear function here. So this one works as well. And actually, if you really are careful with it, this is actually the table that goes with that. Kind of sneaky of them. Next one. All right, so this is terrible. On which of the following intervals is f continuous? Select all that apply. So it could be all of them. It could be, you know, only one of them. But all I have to do is I have to think about, okay, one, where might each of these individual pieces be discontinuous? Where might each of these have holes or jumps or vertical asymptotes? Then, each time I switch from one piece to the next, so at 0, at 3 pi over 2, and at 2 pi, what happens there? Do we have a nice smooth connection from one piece to the next, like we saw up here in this first one? They both met at h of 3 was 9 in each piece. Or do we have this picture where you have a jump between the two? And so we just have to go through piece by piece and consider that. So for my first interval here, from negative pi over 2 to positive pi over 2, I'm only dealing with sine and cosine. So good news there. There's no vertical asymptotes or holes in either sine or cosine. So the only question is, well, what happens at x equals 0? Do they meet each other, thus making continuous, or do they not, and we have a jump there? But sine of 0 is 0, cosine of 0 is 1, so there is in fact a jump. So no. Pi over 4 to pi, well, that's really nice because that's just entirely in this interval here. So it's just cosine the whole time. So yeah, no holes, no jumps, no asymptotes there. It's just cosine. Good news, that one works. But it says select all that apply, so I need to consider the others. Now from pi to 7 pi over 4, Well, that starts with cosine and then spills into the tangent one. And as I think about tangent, I know that tangent has vertical asymptotes at every interval of pi over 2. So at pi over 2, 3 pi over 2, 5 pi over 2, etc. So that's already a problem here. This one is going to be coming down from negative infinity there on the right side of this 3 pi over 2. And cosine certainly isn't doing that. So we're going to have a jump here from 3 pi over 2 to from cosine to tangent as we go from x equals 3 pi over 2 to the other x equals 3 pi over 2 there. So that one's out. And then here we jump from tangent to cotangent. At 2 pi, and we start here at 7 pi over 4 and then go to 5 pi over 2. So when I start at 7 pi over 4, that's a little bit less than this, so we're at tangent there. And then for cotangent, we then start into the cotangent at x equals 2 pi. So the question is, okay, 1, do we meet each other nicely there at 7 pi over 4? And 2, or I'm sorry, do we meet each other nicely at 2 pi? Because that's where we switch. And is there any asymptotes in here? As I consider the first one, at 2 pi, well, they do not meet each other there. Tangent of 2 pi is 0, and cotangent of 2 pi is undefined. So we have a discontinuity there. So again, all you're considering in a question like this is, do each of my pieces have any discontinuities? And what happens when we switch from one piece to the next? Do we have any jumps there? All right. The values of a function can be made. So as you read this thing, sorry, I don't need to read it to you. You're reviewing. You've read the question. This thing is the definition of a vertical asymptote. The values of the function, the values f of x, the outputs of the function, can be made arbitrarily large. The outputs are getting big by taking inputs sufficiently close to 2. Well, that's simply the definition of a vertical asymptote. That's this. Inputs close to 2, outputs arbitrarily large. There we go. This is just a sentence that says exactly that. So we've got this table, kind of like we were talking about before in the table. My first reaction is I don't know what happens in between each of these things. So I have to read carefully and see, did they give me any information about what happens between each of these points? But the question is, which of these, if true, would be individually sufficient to conclude that there exists a number c in the interval such that g of c is equal to 6? Well, what I recognize is my first given output value is -4. My last given output value is 20. This is just some output value in between -4 and 20. So this is an intermediate value theorem question. If you're going to go from -4 to 20, you must cross through 6, but only if you are continuous. G being defined is not enough to make that true. If G was not defined everywhere, this could possibly be true, but the question is, how would we be able to conclude for sure? So G being defined, well, you could have a piecewise function that just jumps right over 6. So that's not enough. G being increasing, well, okay, so to be increasing, we can have, again, a piecewise function that's then technically increasing, but doesn't hit 6 on the particular interval there. It's this one that's sort of the sufficient condition, this one that we've boxed in here already. And then because we've boxed that one, then the last one is, of course, not right. All right, last question. think this is the last question. Yes, last question. So back to the question type from the beginning, just evaluating a limit. If you plug in 0, if you do your direct substitution here, you will get 0 in the numerator and 0 in the denominator. What that tells me is, okay, 1, I have 0 in the denominator, so direct substitution didn't work. I can then try to do some algebraic manipulation, factor, expand, multiply by a conjugate, but I don't really see any of that working here. But what I do see is not just the denominator being 0, but the numerator being 0, which tells me I could do L'Hopital's rule. Remember, you can do L'Hopital if you have either 0 over 0 or infinity over infinity. And L'Hopital says take the derivative of the numerator and the denominator separately, no quotient rule. So the derivative of e to the x is e to the x. Derivative of cosine is negative sine. And the derivative of negative 2x is negative 2. And then 2x minus 2. Now I plug in 0 again and see what happens. Well, in the numerator, I get 1, sine of 0 is 0, minus 2. In the denominator, I get 0 minus 2. So I'm going to get negative 1 over negative 2, which is then positive 1/2. All right, that's all for this one.